everyone to the second session of the IEEE Big Data special session on the forecast. My great pleasure to welcome Lawrence Lizo from the AEMET to provide an invited talk about the near weather forecasting SAF satellite-derived weather nowcasting and data source for machine learning. It's great to have you here, Lawrence. The stage is yours.
Thank you very much. I am Lawrence Lizo. As said, I belong to AEMET and I am member of the nowcasting SAF also team. And I am very happy to share with you this time. And with the presentation, I will try to give you an overview about what is the nowcasting SAF, what are inside our data, and also about the questions that we are facing in our work, daily work, I mean, and how we try to give answer. And also, I will try to make some consideration about how we think that machine learning can help us. So really, there are a great interest in machine learning in our community, an increasing interest, and we are very happy approaching here. I have to say that. So first to say is that nowcasting SAF is not providing data as primary product. We are providing software, and our users are in charge of making the products that you are used. But we are also doing at AEMET because we are also like providing a reference for the users. So briefly speaking, our mission is take the satellite data and derive some fields with physical meaning. So you see that the very simple arrow, but it's not so simple because really it can't work well only with satellite data, and we are including really all of this other information. So we are including like static information like elevation, topography, emissivity, also NWC forecasts, and also another thing that maybe has to be stressed is that some of our products are using as input other products. So it's like a multi-step approach. With all these arrows, we have the risk, or it's normal to introduce some errors. So here you can see briefly a wide range to algorithms and the techniques that are being used. Some of them are using machine learning techniques like precipitation, that I hope I have time. A CTF also is using, and other are more physical based, let's say. So for us, our view on machine learning is that it has potential for us. We are using in some cases, but we feel that is adequate because really our data are very big. Is our images, frame of images, and not one image. We have several channels for image, and in some sensor we have more. I mean, a huge volume of data, really. So for now, the base of the nowcasting SAF, or the more of the product of the nowcasting SAF, is pixel-based. So one thing that we want to explore is how to include more the big features influencing in one pixels, or the textures, or also the influence of the previous states. And we think that for all of this, machine learning can help us. We are using in some products because I am speaking in very general words, but some of them are more, I mean, you see more this potential already. So more consideration to be done is there are some difficulties for us, or we are viewing some difficulties. One of them is that satellite images you have the clouds, and you have also the ground, and you have like a flat interpretation of a 3D field, really. So it's a difficulty. And for some sensors, like I said previously, like infrared sensors, sounders, you have very, very high dimension in the data, thousands of channels really. So sorry. So another consideration that I want to do is when we develop algorithms in the nowcasting SAF, we have metrics to check if it's well performing or is complying with our requirements. But also a part of the testing, like the pod or FAR, let's say, we are also doing like subjective evaluations in many cases or in all the cases. So we see like a risk to exclude this human component of the evaluation of the products. But I mean, I suppose that machine learning is able to cope with this. But for us to have like an automatic method is maybe not optimal, or could be not optimal. Other consideration that we have concerning the features is some of the features are really related with the place that where they are, the orography, you can say. I have put here some examples. I don't know if you can see my wheel, but in the left image you have like a dark line that is called phone gap, and you have in the image more lines, dark lines, but only one of them is this phenomena. And you as human or as meteorologists know this because you know all the context, and in this case you have very high winds from the south. This feature is related to the orography and is producing it's very dangerous for aviation. And in the two other images, we have here in the center fog over a river that is like with a lot of details in the border, and you have snow in the Alps. So they really are quite similar. I mean, in the feature, but you have to know that one feature is adapting to the bottom of the valley, and the other is adapting in the opposite side, that is snow. So maybe the algorithms have to fit with this kind of now data or static data. Also, another consideration is for us, and we think also with machine learning, it has to happen in the same way, is that it's needed that exists a physical relation between the input and the output. Because if you don't have this physical relation, it's very hard to do good forecast or good evaluation of the phenomena. So in this sense, we think that it's useful to search the collaboration between machine learning experts and the meteorologists or remote sensing scientists in the following way. So the machine learning specialists can help in the development of the algorithm to choose the methods, and the meteorological specialist can recommend the input and output variable, and also give feedback on the quality of the forecast, a part of the metrics. So it's about view that how can it works well. I mean, here we have an example illustrating the previous slide. So if we measure the size of the feet of the people attending this workshop, and we try to do a regression between the size and the color of the shirt. So for sure it will end in a failure, or probably will end in a failure, let's say. And if we try to do a regression between the feet size and the age, is more likely to have a success. So we view the problem in this way. So for us to understand all this algorithm, we need to know that there is something related between the inputs and what we want to predict. So now I will briefly go in the algorithms to illustrate what is the situation, or what can be the situation, because a lot of our products are facing problems that are ill-posed. So problems that don't have enough data to be solved without ambiguity. So in order of from less ill-posed to more ill-posed, we have, as an example, these three algorithms that we are producing. One is for the cloud top and temperature, right? So it's trying to evaluate which is the height of the clouds. Another one is in development, but is exploiting infrared sounders and trying to do a profile. And the other less or worse posed problem is precipitation, that is not so very well defined. So we will go quickly. So concerning the PPS algorithm for polar satellites, that is taking care of CPTAs, the height of the cloud, the sensor see the temperature, let's say, the brightness temperature. So you understand that when the cloud is very cold, it's higher. So there is a relation. For this, we are using already some machine learning, that is a convolutional neural network, and we are using also numerical weather prediction data. So part of the algorithm is taking care of the texture in a let's say simple way, and the other is taking care of the pixel measurement acquisition. So the architecture is this. You see that it's not very complex, but it's giving us good results. You have here a comparison, and we have learned also that they are you can train in a sensor and apply another sensor, and it's not so bad, it's good. So you have here another example of product that is in development, because it's not flying already. There was sensor, or just stationary sensor almost. And we are developing based on YASI, that is a polar satellite. So it's doing a spectrum of a lot of frequencies of the light that the satellite can receive. So based on this, you can derive, not univocally, but you can derive the profile of temperature. But you have to use more information that is called background. You have to use numerical weather prediction in some cases. And for this algorithm, we are choosing kernel registration, because we are aiming to do a rolling calibration. So we can rely on artificial networks that takes more time to train, because our idea is to have like a rolling recalibration of the kernel. So this one, we have like station, and here some of the results that are not so bad, are really good. So, and the last algorithm that I want to tell to you is the precipitation algorithm. The precipitation is very indirect. It's not so well correlated with the radiances of the satellites, because the satellite is seeing the top of the clouds, and you are trying to forecast or to diagnose the precipitation above, and you can have a similar clouds giving precipitation or not, similar temperatures, let's say. So for this, we are using now all the channels at day and combining with a product that is cloud water path that is previously calculated. And at night, we are simulating the visible channel in order to use the same algorithm. With this, we do a dimension reduction with principal components, and after we apply a root directly. Is the more simple. We have not applied any kind of neural network. Sorry. So, but it's working very well, or almost, we think. We have here in the left, we have the satellite estimation, and here in this example, the radar. So they are quite good, really, for the difficulty of the problem. And here is at night. So now, in the last slides, I will try to give you a context on where are our data. So we divide in the data, like you see, is level 0, is from the satellite. After it has a processing to compose these radiances that we and the Untitled SAF are using. So in this sense, we are not that the satellite is looking at. We are calculating above of it. So it's known as level 2 products. So they are products that are in the same grid that the satellite, but are derived. So we hope to take advantage of the machine learning technique, or the most advanced in this step, in the step of doing our algorithms. A consideration is that we have a time requirement, so it has to be very fast to apply. And also another difficulty that we have is that we are developing in C still now, and we have to change maybe to Python, but it can be solved. And also another idea that we have, another thought, is our products, the no-cut products, can be used as data preparation for specific problems. So they can be used also as input for machine learning algorithms. Really, we are in somehow doing this because now our product takes the radiances or some of the radiances and takes, by example, the cloud mask to derive precipitation. So we are exploiting already this schema, but we think that our products also can be useful for this data preparation. By example, if you want to know where is cloudy or not, is straightforward through our products, really. So we propose like a combination maybe of something like that. And another interesting field that we need to explore is the fusion of data, because, by example, we have precipitation derived, and we have other data sources that are not really in the same grid. That, by example, CML, that is precipitation derived from the links between the antennas of the several phones. So we want to explore how or if machine learning can help to fuse these two fields to obtain something better. I mean, or maybe to extend the radar coverage or to extend the CML coverage. So we see another potential in data fusion, really. And the last slide, just summarizing. Some of the nowcasting staff are already using machine learning techniques, so it's not totally new for us. But more important, we think that other nowcasting staff algorithms can benefit with these techniques. By example, CNN for precipitation. We have a visiting scientist for this the polar side very soon. And also another point that we want to explore is using this nowcasting staff data as data preparation. So to feed some machine learning algorithm for forecast, I don't know, fogs or stuff like this. And also we want to, we see potential in this data fusion, in how to fuse the data for very different sensors or different estimations really in one single product. So thank you. It's all. I have ended. I am open to questions now.
Thank you so much. We have a question by Pedro Heruza, who comments on the human in the loop and wonders whether you have any annotated data sets that highlight these challenges as you've shown in the north of Spain, where you have so similar features, some are snow, some are cloud. This would be actually a nice challenge for machine learning to test the boundaries. Is there anything like that available?
I'm not sure because I'm not hearing you very well, but in this respect, we for us, for web development, we are doing the following. We train the algorithm with 1 year, by example, for precipitation, and we try to meet these pod and far requirements. But apart of this, we have another person, or the same person, in this case is another person, that is looking at the outputs for winter in north regions, and we are looking if they have a good aspect, or if they have really, for some cases, a very bad behavior. So it's like, and when we detect this, we try to improve the algorithm. That is, I'm not sure if in machine learning it's possible to do with this strategy, but by example, for precipitation, we have this crude algorithm, and after we are adding decision trees to filter the bad behaviors, let's say. We are including after these floods that you've seen, a filter that is filtering all the areas with very high stability when we don't expect to have really too much rain. And we are adding more information using numerical weather prediction for this filter.
Thank you so much for the fantastic presentation. And we're moving on to the third prize of the competition, where Park Hai-Kwok and Kichi from the UK will present their enhanced variational unit for weather forecasting. I look forward to your talk. Thank you.
Hi everyone, so my name is Chi, and I'm presenting on behalf of our team, Microfiche Forecasting, and I'm presenting our enhanced variational unit for weather forecasting. So Ivan couldn't be with us here today, so it's just me. A quick intro to us. So there's two of us in this team. We met, so we first got involved in this competition because we took part in the traffic forecast competition last year, and we thought there were some similarities. So we want to see if our solution for that could be applied here. At that time, we were both working for Rolls-Royce and as engineers, and it really, we were quite interested in machine learning, and we both since moved into machine learning companies. So Ivan has joined as a data scientist at TfL, and I've joined a machine learning startup called Second Mind, which focuses on automotive applications using Bayesian optimization and Gaussian processes. So the competition, so this I mentioned, I think many people mentioned before, it's a continuation from the stage 1 competition. So the data structure and the sort of the problem setup is very similar. We have our 4 training for data from 1 hour, and then we're asked to predict up to 8 hours ahead. Each frame, each data can be seen as an image, with width 256 and the height 256, and the channels have sort of different types of weather-related data. And the key difference is in this competition, we're given some extra regions to predict on. So you can see the map here that I've already shown. So the extra regions are region 7 here and region 8 for the core competition, and then region 9, 10, and 11 for the transfer learning competition. So a bit of background to our model and where that came from. So as I mentioned before, we took part in the traffic forecast competition, and we used a UNet there. And obviously that model, that UNet, was inspired by lots of medical image segmentation work done by various people. We then also took inspiration from variational autoencoders, which have proved quite popular in literature. And we thought that combining these two might help us tackle the more, what we felt was more random nature of weather compared to the traffic. As such, we replaced the bottleneck of our traffic forecast unit with a VAE, and the intent was, to make the unit probabilistic while maintaining the ability of the unit to learn sort of fine-grained details. I won't go into this too much, but this is a sketch of what a sort of unit looks like. And this, so our unit looks like, but this is, I guess quite familiar to anyone who's seen these schematics of units. But the key difference here is we've had some sampling layers here, which introduce this sort of variational nature of it. In terms of what we learned from stage 1, we ended up with, so we did do some experiments with using one model for all regions, as well as multiple models, so models for individual models for the regions, and we found that training one model was better. We thought this is because our model could handle more data, so having more data was just making our model better. And we also, so this hypothesis was not confirmed, but I guess further suggested when, at the end of the training phase, we trained a further 2 epochs with the validation data, and this actually gave us a 0.7 improvement on the leaderboard. So it did seem that, adding more data was better. In terms of the variables that we use, so this is completely unchanged from our stage 1 solution, but I thought I'd recap them. So obviously we are being asked to predict 4 target variables: the temperature, the convective rainfall intensity, the probability of tropopause folding, and the cloud mass. But we also, with some experiments during stage 1, we added some of the other data that was available to us, but we didn't have to predict. So specifically the pressure, the rainfall accumulations, the cloud type, and also we added a mask stating whether the temperature was coming from was being measured at cloud top or ground temperature, as this feature is actually a combination of both temperatures. So that was our summary of our input and output variables. We also did use the static data, so the longitude, latitude, in both competitions. We didn't really think about not using them, but perhaps in hindsight, having seen some of the page, I'll mention that later, maybe that would have been a good idea. So obviously, we're trying to use sort of image type approaches. So we did the trick of collapsing the time dimension into the channels. This allows us to use sort of imaging techniques such as the UNet. I've already mentioned that I think one of our key points from stage one is that we felt that more diverse data or more data might help us. As such, we this time around, we applied a load of data augmentations to increase our training data size. We basically picked the easiest augmentations we could implement. So vertical flips, horizontal flips, and then various rotations. And the good thing about these was no padding was required. So everything and everything else just stayed the same. So we're just changing and increasing our data size up front. In terms of loss function, so similar to stage one, this is exactly the same loss function as what we had in stage one. And again, because of our model, it has two parts: the reconstruction bit, which is as close to the metric that we get told the leaderboard is being evaluated on as possible, and also the KL term, due to the variational nature of our network. We had this factor which weights them, and this factor we kept the same from stage one to stage two. We didn't experiment with it, but it seems to work pretty well, which is, I guess, we hope reassuring. So we've not like over tuning that parameter. So we approach this aside from data augmentation. We approach this in sort of another way, in the sense that we wanted to use some transfer learning. So our model from stage one is already trained on most of the regions. So it felt like that model must have already learned lots about weather in general. So instead of starting from scratch, we carried on training that model from the weights we already had. And then we actually did this in two steps. So first of all, we just trained them on all the regions, so the stage one regions plus the stage two regions, and then we also added data augmentation later. We also did a separate training regime which completely started from scratch. So this is training on all the regions, stage one and stage two regions, stage two regions which contains both of them from the start, as well as data augmentation. And finally, at the end, we did some model blending from our model A and model B to do for our final predictions. So in terms of the results, so if we look at some of the loss curves, the training curve. So on the top left here is the training loss, and on the right is our sort of validation score, internal validation score, and the bottom is the leaderboard score. So if we look at the training one first, so you can see that for our model A, which is the one that we did some transfer learning on, it starts at epoch 12. This is because the first 12 epochs was exactly what was done in stage one. We take that model over, we take those weights over. We now train the model on all the regions, and we did this for around 8 epochs. At which point we then switched on the data augmentation and then continued training till completion. Whereas the blue one is just completely from scratch. So from the start here, there was data augmentation, there was training on all the regions. And then over here, you can see the validation loss. And I guess the key thing here is they follow each other quite closely, which is nice to know that they both seem to work equally as well. Which is reassuring, because basically it's saying that we didn't have to throw away that model, we can just carry on, and if we want to predict more regions in the future, just carry on training on those as well as your previous ones. That's what we thought. And here is the test leaderboard scores of the two models. The top two here are for the core model, so you can see that B does eventually get better, but I'm not sure how differentiating that how much you can conclude from that. And the validation, the transfer learning ones, they remain very much quite similar. So this looks at the summary of all the models we use in our final submission. So this table basically summarizes it all. Here we have our, for the core challenge, and then the transfer learning challenge. We have our validation score, and then the test and the final leaderboard scores. The first one we mentioned here is the baseline, and then A means model A, which is trained in that sort of transfer learning approach. So we have, and then the 30, the number here means at what epoch this is being evaluated at. So this shows, our final models, and then we did some experiments with blending them, and we found that, combining models weights, well, combining predictions from model A and model B actually gave us more of a benefit. So in the end, for the core one, we ended up basically combining our 3 sort of best or most trained models. And for the transfer learning challenge, we ended up using 2 from A and then 1 much earlier on from B. And I think Pedro, thinking about this before as well, when Pedro mentioned that compared to the second position, our transfer learning score was relatively worse. And we're thinking, I thought, why? And perhaps I wonder if it could be related to using those static regions, because if we looked at the map, the longitude and latitudes of the new regions were quite far beyond what the core challenge contained. So perhaps there's something to do with that. We're not sure. We can look into that. So in terms of conclusions, the first conclusion is that this variational unit demonstrates its capability and robustness in weather forecast. So we made no changes to the actual fundamental model, just the things around it. We showed it was possible to carry on training, and that didn't really, there was no sort of negatives from that, which is quite nice. So you can just carry on training a model with new regions without having to start from scratch. We found improvements from model blending. And again, I think this showed the importance of having a robust validation strategy and not being over-reliant on a single metric or a single data set, especially with weather. And then we thought, another thing that we thought, looking at some of the other contestants, whether perhaps we should have done a dedicated model for each of the products, as Jussi showed in his sort of stage 1 winning solution, which is carried on to. So that concludes my presentation. Happy to take any questions.
That's great. Thank you so much for the really interesting talk. Are there any questions from the audience? Maybe I can start in the meantime. You mentioned you were interested in seeing how more data would improve the model. And I was just wondering, did you try in any way to dissect this question of more data or more diverse data by subsampling to equal sizes, but with more diversity or so? Did you look into this at all?
No, yeah, unfortunately didn't get a chance to, but I think in stage 2, what we did find was the trick of training on doing a few more epochs on the validation data didn't give any benefit in stage 2 compared to it. In stage 1, it was significant benefit. So I guess the data augmentation and the extra regions just meant that our model was already like taking as much as it could handle, perhaps.
Okay, but you could test this by trying to make the model a little bit smaller, right?
Yeah.
So, okay, thank you very much. Are there any other questions? Yeah, Mario Kren is asking regarding your approaches to data augmentation. If you could elaborate a little bit on that, firstly on how and what you did, and also what percentage of your data was augmented.
Yeah, so I think these were, at every time we had it was a random chance of whether we would horizontally flip it or not, like 50-50 chance. Same with vertical, 50-50 chance we would flip it. And then there was a 1 in 4 chance of whether we would apply some rotation to it.
Thank you. So Pedro Herruzo is thanking you for the nice presentation. He liked the ensemble using different snapshots, and he's asking whether he understands correctly that you can also sample from the variational unit, and if that's right, and if you've tried that.
we haven't tried sampling from it. We just use the mean. We just use the mean values. We haven't looked at what the actual so when we predict, we just use the mean. We don't do any sort of sampling, if that's what you meant.
Okay. Does the distribution perhaps tell you something about the quality of the fit?
I think I'm sure it might. Well, hopefully it should do, but we haven't looked into that. But that's definitely something we can look into.
Cool stuff. Thank you. So Mario Kren is asking if there are other simpler types of data augmentation that could help. Your thoughts about that? Why did you do it? Just how you did it? Would there be other approaches?
Yeah, I guess it's trying to keep it both simple and physical, right? Because it feels like, a vertical flip, the physics in the weather would still make sense, or because we're flipping everything, right? So that would make sense, I guess. If you started changing the actual, if you started stretching it or things like that, I don't know whether the physics, whether you're overstretching. So these were like sort of the easiest things that we were pretty confident didn't break anything.
Okay, fair enough. Okay, I think we need to move on to the next speaker. Thank you so much, Chichi. The next speaker is Alabi Bojizoma from Khalifa University, and he will present his paper submission on a spatiotemporal vision transformer for short-time weather forecasting.
Hello, everyone. My name is Alabi Bojizoma, as introduced, and I'll be presenting our experiments on the weather forecast stage 2. The title of the presentation will be on spatiotemporal vision transformer for short-time weather forecasting. As an outline, I'll be talking about some short introduction to the challenge. Of course, this one will be minimal since everybody has been talking about this. A little discussion about vision transformer, the kind of transformer that we use for this work, which is a shifted window-based transformer, our model architecture, the result and findings, and finally I'll be concluding the talk with some observation. To start with, as an introduction, the challenge that we are trying to solve is spatiotemporal in nature. As we know, the data involves some kind of number of frames of inputs. Specifically, we are going to work with 4 frames of. Specifically, we are working with 4 frames of input, which is 15 minutes per time step, and we are planning to predict 32 frames, basically for 8 hours of future frames. Because of the kind of this data being that the challenge being both call and transfer, there is a need for us to put into consideration a model that can easily be generalizable. So which is the reason behind our choice of model, because for these attacks we use a spatiotemporal vision transformer, which involve using 3D swine transformer, not the regular transformer that is spatial, but in this case we consider this temporal dimension as well. As a slight introduction to transformer, I've discussed this thing in my previous talk, but I feel like it's worth mentioning again. Transformer is normally unique to natural language processing. And based on the quality of work that has been done with transformer in natural language processing, there is a new trait of research that are looking into benefiting from transformer for computer vision tasks, specifically because of the interrelationship between the tokens. So we can have a kind of a good interrelationship between a particular region of our spatial data and any other region. So this one can encourage a global form of filtering as compared to CNN that is always locally based filters. Based on this, some kind of transformers have been well used in vision. majorly the full attention normally gain a lot of interest based on the being full attention. We have a relationship, a long-range relationship. However, this normally come at a kind of a challenge, which is basically the computational challenge, because images tend to be high resolution sometimes, and when they are high resolution, so we cannot imagine considering long-range interaction between pixels that are like 512 by 512. So this will be quite challenging and computationally intensive. This is the reason behind some form of transformers like this one on my slide, which is a shifted window transformer. And the concept in this one is just that, more like CNN, we are going to deal with them in a layer-based. A particular stage of our network will be focusing on some kind of smaller windows, where when we go to the next stage, we are going to make the window more broader. However, we are going to do some kind of resolution reduction, something that we normally use max pooling and the likes for. So this encourage high long relationship at the later stage, which is formal quast, and is going to have some kind of minimal relationship, just like a window-based relationship at earlier stage. And this is actually what we expect in a normal network, because we cannot imagine dealing with weather condition. We want to say that just at the start of our network, we want to find the relationship between a particular pixel and some distance far away. We want to limit it to some kind of region. So as for this kind of transformer as well, when we have a particular layer being window-based, as you can see here, this window here involves like 16 patches. So each of the patches here will be related together with the transformer that we use. However, just the next layer, we tend to shift the windows around. This is going to encourage relationship between the different windows as well. And also on this slide, looking at the lower figure here, it's specifically focusing on a 3D shifted window. And this is important for this task that we are dealing with. When we are dealing with a network or image or inputs that are actually three-dimensional, like spatiotemporal, so there is a need for us to not only deal with the relationship between the spatial dimension, we have to consider the temporal dimension as well. And this is where this 3D shifted window is important. As we can see in this box that I'm highlighting here, we will see that we have a T by H by W, which the T is the temporal dimension. So in this case, if we try to divide this one into several patches as we have here, it implies that a single patch involves some kind of a spatial window as well as some temporal dimensional part as well. So we can have this kind of patches, and within this single patch that we have here, or single window that we have here, we're going to have complete relationship. And different blocks here have complete relationship as well. But when we go to the next layer, we try to shift these 3D blocks a bit to encourage some kind of relationship between a block and some other blocks close to it. And this is something that is actually expected when we are dealing with regional-based information like weather, because we expect that just like weather can be related to flow, so we expect that the weather condition at a particular region will have influence on some other region, maybe after some period of time. Based on this kind of shifted window attention, we design our model. Our model is more like a unit more like a small unit in nature. The only difference is just that we don't use any convolutional blocks in this model, except within the path partitioning. That is that when we try to generate patches from our input, that is the only place where we use anything that involves convolutional layers. Every other thing that we have here as based on transformer architectures, and also we normally have linear layers in this. Specifically, we have fully connected layer here. As you can see here, we have 3 stages in the encoder and 3 stages in the decoder. And for the encoder and decoder, we basically use the Swine transformer for the encoder as well as for the decoder. And the only thing that is important, the other thing that is important here is that the inputs that we are having is spatiotemporal, and we expect that we have time axis following the depth, height, and W. But just before introducing it into our network, we transform this thing to be to have our time axis to be closer to the H and W. That is why each of these translations have the T followed by the H and W divided by the partial that is gradually dividing the network here. So at this point here, we have the dividing the resolution by P. The next point here, we divide the resolution by 2P, and gradually we divide it and so on and so forth here. While in the upsampling part, we actually go backward from what we did in the encoding part. For this network that we have here, we basically train a single model. And our single model is in terms of the input and output. That is, since we are meant to train and get results for 4 different target variables, a single model is trained to get these 4 different target variables. And it was trained by with all the data from all the available cities at once. We don't have a city-specific model, neither do we have a target-specific model. And beside this aspect of our training, we also use some kind of augmentation. And the reason for our augmentation is because we noticed that for us to train a transformer-based model, it's usually something that is data hungry. It requires a lot of data for us to train it well. And to do that, we need to look for a way of generating some kind of new types of data. So which is why we use this augmentation. And since we don't want to change any kind of nature of the input, that is why we limit our augmentation to flipping and rotation. Because since we have a square spatial dimension, 90-degree based rotation will not have any update on the data, except that the axis will be updated. Also, the flipping is not going to have any kind of a new trait of input. So we use this thing for our augmentation. However, for our data that we consider for the training, for all of our models, we train with the target variables. Specifically, we have the temperature, the rain rates, and the other 2 that we have here. Basically, those ones that I have in bold here are always in any model that we train. But we also consider some kind of input beside these 4 as well. All the ones that we have in italics here are actually considered in another model. We for some reasons, we decide not to use anything that involves the data quality, like the ISAIA quality here or the CRR quality. Anyone that involves quality here, we don't use them in any of the models. But for a model, we considered using all the other variables besides the quality for the dynamic, as well as considering the static variables in the training. For the results here, we have 2 models trained, one of which was trained with all the available data except the quality-based data. So we train it with the static data, the target variable, and the other variables available besides the static, besides the quality-based information. While the other model was trained with only the target variable. And the reason, as well as the observation from this kind of training, is that we notice that the dynamic data is enough for transferability, and as is not going to overfit the model too much on the the location-specific information, like the static information, which is location-specific. So we notice that we don't need this thing to have a good transferability. And we train one model with all the data, while we train this one with only the static, only the target variable. Based on our training, and we have these results, because we have two models. The first model, which was trained with all the available information, is the one that performed best for the core challenge. This is as expected because we train it with both the static information as well as all the available information. But this thing can be a little bit overfitting when it comes to transferability. This is why we notice that it's not having a good transferability compared to the second model that is trained with just the target variable. Because the one that we train with only target variable is the one that performed best in the transfer challenge in our experiments. As a bit of conclusion, we present some kind of a 3D-based swine transformer in a unit-based model for forecasting, and we also considered using this thing, incorporating spatiotemporal interrelationship of region-based data. This is why we use a swine-based transformer, basically because of the window-based attention. So we are able to have a region-based interrelationship. And based on our training, we observed that our model is quite parameter efficient, because none of our model is more than 5 million of parameters. And even with just 4 million parameters, we have a good transferable model. And also our experiments show some kind of trend in terms of being that static data is majorly important for core-based data, that is for core challenge, why it is better to leverage on all the available data when we are dealing with specific regions, that is the core-based challenge. But we should only focus on the dynamic nature of the data when we are dealing with transferability. So as a bit of future work, we plan to do more on a model like the model that we trained with just the static data. We want to see how it's going to perform when we train it with the model where we train without the static data. We want to see how it's going to perform when we consider the static data for this kind of model. Because the model, not only was it having a difference in the data that we use for them, it also have a bit of difference in the hyperparameters used. Because the one that we use for transfer has a little bit of a lower parameter, because we don't want it to be too big to avoid overfitting on the training information. And this is a conclusion of our experimentation on the traffic forecast stage 2. Thank you very much for your time, and all questions will be welcome.
Wonderful. Thank you so much, Alabi. We already have a question from the audience by Christian Eichberger, who mentions that you have used a similar setup also in a completely different domain, modeling traffic in the traffic forecast competition. And he's wondering if there are any differences in the architecture of your models, and if so, which ones and why? And he's wondering whether you have a feeling for how the same setup works for both problems, if it is the same model, and if there are differences in the model, if you can maybe explain a little bit about them.
Yes, thank you for that question. Actually, what we observe is that because traffic data is more sparse compared to weather data, so for this particular weather data that is a little bit more dense, it is better to avoid too much of parameters. In essence, If you look at the dimension that we use here, we ensure that we use a constant dimension for all the levels. Because we have 4 levels in the encoder and decoder here, we still maintain a constant dimension. But when we are dealing with traffic data, when we try something like this, it's not really performing well. We have to use we have to update the dimensions. Let's say from here, from 128, I have to move it to 256 and the likes. But here that we have dense information, so I don't need to worry so much about that. The information is there. So in this case, we can actually deduce the dimensionality of the network, where the network is going to have enough information to train itself with. So that is one thing that we observe in this setup. Another thing that we also did was that for this particular setup, we don't do much of fixture mixing or fixture matching or anything. We don't do any kind of processing on the features. We only get the data into the model from the beginning. We have the data at this point. All we have to do is to change the location, to transpose the dimensions from D and T. That is all we have to do for us to be able to use this kind of part partitioning. All we have to do is to have this as our last 3 dimension, the temporal domain, the temporal dimension, and the spatial dimension. But in the traffic, we still have to do some kind of something like more like a pre-processing in the learning itself to be able to work well with it. But for weather forecasting, we don't need to do any special thing than just to present the data in this format.
Thank you very much. Are there any further questions? I think Christian Eichenberger also was curious whether you could say whether the static variables, say the topology, helped in a similar way in both application domains, or whether there was a qualitative difference in the 2 scenarios.
Yes. Actually, for the scenario of traffic, if you are to use the static information, we don't choose that. We don't train any model with static data as at yet for the traffic forecasting data, because we believe that the data is so huge. There are a lot of data. We even have some that we don't even use at all. Because one of the reasons why we try to use this kind of extra data like static and like is to have more information to train with. That is the motivation behind using this thing, to have more information to train with. And if we have more information at the moment, we see that we shouldn't start our experimentation with that. But we plan to do this thing in our further studies, like to use static information for the traffic forecast as well. Because we don't do anything like that for traffic forecasting. We only use the static data for masking in the traffic forecasting. We don't use it for any part of the main data training.
Okay, thank you very much. It's impressive to see that the same dynamical approach works so well in so different domains. So thank you again.
Thank you so
We'll now move on to the closing keynote lecture of the day, ending this session. It is my very great pleasure to introduce you to Piotr Demirovsky of DeepMind in the UK. His work has been pushing the state of the art in as diverse fields as epileptic seizure prediction, the response of gene activity regulation, and more recently, advanced navigation in real-world environments, verbal and visual language, and last but not least, the accurate nowcasting of local precipitation. So I'm delighted that in today's closing keynote lecture, he will share his insights on how skillful precipitation nowcasting using deep generative models of radar can overcome the typical blurring and poor prediction performance of classical deep learning predictors for less frequent medium to heavy rain events. So without further ado, Piotr, the floor is yours. I really look forward to your talk.
Thank you, Professor Krau. And good evening, everyone. Thank you for still being there at this time. And it's really delightful to be joining this virtual panel. I love the keynote session and then all the submissions and the discussion about satellite data. I would like to also thank Professor Alexandra Golca for inviting me. So, my name is Piotr Mirowski, and I'd like to talk about skillful precipitation nowcasting using deep generative models of radar. And sorry, I'm just throwing my mouse around my table. That's making lots of noise. Well, so as you said, I work at DeepMind, a research lab in AI that is part of Alphabet, and like several of my colleagues, I'm interested in application. Oh, did I forget to share my slides?
So far, yes.
Yes! I was so excited. I'm so sorry.
No problem.
I guess I need to do that.
Please do.
Yes, here are the slides.
Now we see everything. Thank you.
Thank you. Okay, so I'm not going to go through the beginning again. Go straight to the matter. So I work at DeepMind, a research lab in AI, right? That's part of Alphabet. And like several of my colleagues, I am interested in application of AI to the real world. And for this project, we needed a partner and additional expertise. So we joined our forces with the informatics lab at the British Meteorological Office, the Met Office in short, which was founded in 1854, and which has pioneered the science of meteorology. So a little anecdote is that the Met Office is responsible for moving the date of D-Day from the 5th of June 1944 to the 6th of June 1944 because of unfavorable weather conditions for the Allies. So anyway, in this project, our aim was to combine our strengths as two research-driven organizations to build a deep scientific collaboration. And it was a wonderful learning experience, as we have met multiple times a week, every week for the past 3 years. We started with initial meetings at the end of 2017, scoping the questions related to weather forecasting and to climate, confronting our approaches, machine learning versus numerical weather prediction models, and finding that precipitation nowcasting stood out as a perfect opportunity for applying machine learning techniques. And after a couple of years of research and that involved lots of writing and revision process, we managed to publish our work in Nature. And this presentation covers that specific work from the perspective of a researcher in machine learning. So this talk will be in 7 parts. I will start with a statement of a problem. Precipitation nowcasting. We know that precipitation nowcasting is the high-resolution forecasting of rainfall up to 2 hours into the future. It is crucial for weather-dependent decision-making. Nowcasting informs the operations of a wide variety of sectors: flood, early warning systems, air traffic control and marine services, emergency services, energy management. And we believe that the nowcasting problem is interesting from a data science perspective for 3 different reasons. First, for nowcasting to be useful in all those applications, the forecast must provide accurate predictions across multiple spatial and temporal scales. Second, nowcasts must account for uncertainty and be verified probabilistically. And third, nowcasting must perform well on heavier precipitation events that are rare but critically affect human life and economy. As you may have guessed, I worked focused on the UK. Our nowcasting models were trained and evaluated on data from a collection of Doppler radars from the Met Office Radar 4 network, which comprises more than 15 operational radars covering 99% of the UK. And we can imagine that data as a grid of 1536 by 1280 pixels, where each grid cell of that composite image represents the surface level precipitation over a 1 kilometer by 1 kilometer region, expressed in millimeters per hour. The UK uses a custom projection and coordinate system, which is centered on the UK. And thanks to the Met Office data provisioning team, we're given radar composite images every 5 minutes since early 2016. So that is a few terabytes of data. We are definitely in a big data regime with a data size that is dwarfing the size of MNIST digits or ImageNet samples that many of us grew accustomed to. We also assessed the generalization of our techniques by retraining our model on slightly different data from the continental United States using radar composites from the multi-radar, multi-sensor MRMS system, and acquired with a network of 146 radars covering the USA and 30 Canadian radars with 0.01 degree resolution, which is about a kilometer for each step of latitude, and it changes between 1.1 to 0.6 kilometers for longitude. MRMS data, however, was not as nice as the UK data. First of all, nobody will be surprised if I say that it doesn't rain as much in the US as it does in the UK. Rain is a cultural phenomenon in the UK, and according to the BBC, there is a study saying that 9 out of 10 Brits have discussed weather in the last 6 hours, and I guess that doesn't include sleep. But more seriously, we noticed that precipitation nowcasting, precipitation dynamics data in MRMS presented skipping patterns with measurements from different radars that were updated asynchronously every 2 minutes, which was not great. So we reduced the effective temporal resolution to 6 minutes to mitigate this skipping effect and to make the temporal resolution also comparable to the UK dataset. Now I need to say a few words about Ensemble numerical weather prediction, NWP systems, which simulate coupled physical equations of the atmosphere and generate multiple realistic precipitation forecasts. NWP would be a natural candidate for forecasting, as one can derive probabilistic uncertainty estimates. But our nowcasting horizon of up to 2 hours is limiting for NWPs, which provide poor predictions because 2 hours is essentially less than the time needed to spin up the model, and also because of difficulties of data assimilation of radar into NWP models. So the only way in which we use the UKV deterministic forecast product, specifically the rain flux, was as a baseline. Then there were also rain gauges, but data was messy and we just used it for calibrating radar. And surprisingly, orography and land cover was not really needed to achieve good nowcasting results, probably because of the conditional independence given recent radar measurements. And finally, unlike the MetNet study, we did not use satellite data. So let's skip to baselines. Steps and the corresponding open source Python library PySteps are industry standard models for probabilistic prediction nowcasting that rely on multi-scale optical flow. The optical flow is estimated from the most recent consecutive radar images with some smoothness penalties and used to define a 2D motion field called advection field. Using that advection field, we can extrapolate, using semi-Lagrangian extrapolation, the most recent radar images to make predictions. Because of the application of stochastic perturbations, both of rainfall intensity and of the motion field, we can obtain different realizations for ensemble nowcasts, from which we can derive probabilistic and deterministic forecasts at multiple timescales. Early in our research, we tried to improve upon the optical flow-based methods by trying to learn a differentiable approach to optical flow. We use state-of-the-art PWC nets, as in pyramidal warped cost-volume networks, which work well for learning to estimate optical flow from sequences in an unsupervised way using simply consecutive images. The problem was the boundaries of images, where information was missing. The neural network would find creative ways to make up predictions, basically smudging the edge of the image, which was not at all physically plausible. We ended up not using PWC nets at all. Our second strong baseline was the unit encoder-decoder model, used by several of our colleagues. And after extensive exploration of units, we made some architectural and loss function changes to improve their performance at longer lead times and heavier precipitation. First, We replaced all the convolutional layers with residual blocks. We used 6 residual blocks that provide a small but consistent improvement across all prediction thresholds. Second, rather than predicting only a single output and using autoregressive sampling during evaluation, the model would predict all frames in a single forward pass. And that mitigated the excessive blurring that we found in the literature and in our own experiments, and improved somewhat on quantitative evaluation. We tried both regression and classification losses on units. But there was still a problem. Even though units would outperform traditional optical flow methods in terms of metrics, they would produce blurry predictions. Okay, so that we tried a second baseline, a second deep learning baseline. Earlier today, we had a fantastic talk by Nal Karlsbrenner about the MetNet model, which was our strong state-of-the-art baseline. MetNet is a combination of a convolutional long short-term memory encoder and actual attention decoder. It was demonstrated to achieve strong results on short-term low-intensity precipitation forecasts using both radar and satellite data on continental USA. MetNet makes per pixel probabilistic predictions, and it factorizes spatial dependencies using alternating layers of the actual attention module. We adapted the actual attention model from MetNet to our setting, paying attention to have the strongest competing baseline. First, because we operate at the same scale as MetNet, which is 1 kilometer per pixel for UK data and 0.01 degree per pixel for US data, and because we're making predictions at horizons of only 90 minutes, we could reduce the input window, assuming rain cloud maximum speed of 60 kilometers per hour. That essentially meant margins of 96 pixels. So 256 by 256 inputs with 64 by 64 outputs. We didn't need a spatial downsampling. Then we reduced the temporal extent of the input context from 7 frames, 90 minutes with 15-minute intervals, to 4 frames covering 20 minutes, 5-minute intervals. We also didn't have access to geostationary satellite data for the UK, so we conducted our study using only elevation, position, and time embeddings. However, and counterintuitively, we observed that this additional elevation, positional, and temporal embeddings did not improve performance, and changes in metrics were not statistically significant. And we hypothesized that at the time scale at which nowcasting operates, the phenomena represented by these additional embeddings are modeled in the dynamics of precipitation of simply 4 input frames. Also, we rescaled the targets of the model to improve its performance on forecasts of heavy precipitation events. But to no avail. Even though we managed to get very good performance in terms of metrics, and I'll go back to these details later, there was still a problem. The predictions were blurry. What happened? I'm going to explain the problem in 3 different ways. And the first way is going to make use of the language models. It's a bit of a crude analogy, but I personally like my language models, and also the construction language models are autoregressive, and they make use of past information in a proper way. So I decided to use DeepMind's latest language model called Gopher, recently published last week on Archive, and I fed Gopher the following prompt, which is precipitation nowcasting. The high-resolution forecasting of precipitation up to 2 hours ahead supports the decision-making processes. So each of those word tokens is generated by sampling from a probability distribution over possible tokens. For simplicity, we can assume these are word tokens as opposed to character diagrams. A different realization with the same prompt could be increasingly important issue of flood. And every time the language model generates a token, it feeds it back autoregressively as a context to the next sample. And these probability distributions are calculated on the fly during the generation. So this is a third generalization. What's important is that these probability distributions of the words are not computed jointly, in parallel, and ahead of time. They're computing step by step. It would not make sense to sample independently the words increasingly planning processes, because it doesn't take into account the autoregressive nature of the model. Okay, so that was explanation number one. Number two, how does language modeling and generation relate to our problem of precipitation nowcasting? So recall that the UNet and METNet models that I described earlier were making the following assumption for modeling the optimization objective. Joint probabilities over all horizontal and vertical pixels of a generated image, in some cases computed over all time steps, with poor assumptions about conditional independence given the context. The optimization process would optimize the mode of a distribution, but would nevertheless assume conditionally independent Gaussian probabilities for mean square error regression or conditionally independent multinomials for classification. So conditional independence boils down to, in the case of, let's say, two grid cells, the orange and the green one, to the following. If you are given a context input, previous radar information, then under conditional independence assumptions, if we know about the future value of a green pixel, that doesn't help us make a better prediction of the value of the orange pixel, because the input context has factored out the conditional probability. And yet, the green and the orange pixels are related because of spatial correlations, because they are in proximity of one to another. So the problem is that even if we manage to train UNets and METNet, and even they get good performance metrics, we cannot actually sample properly from those distributions. And that's a problem once we acknowledge that the weather data is inherently stochastic. Let me say the same problem a third time, this time using a thought experiment that we ended up not including in our paper. A heavy precipitation front, 30 millimeters per hour, so heavy rain, very localized, is moving over two different cities, either London or Brighton. Brighton is on the coast of England, not far from London. And that means that at time 0, our estimates of the probability of rain in London at time t plus 30 minutes is 0.5, and the estimate of the probability of rain in London in Brighton at the time t plus 30 minutes is also 0.5. We don't know. But now let's assume that at t plus 30 minutes, we observe that it is actually raining in London. What does it mean about Brighton? Well, because we have a very localized precipitation front, it's probably not going to rain in Brighton at all. So now the problem with conditionally independent models is the following. The regression model will say it will rain at 15 millimeters per hour, both in London and in Brighton, taking the average. Because of uncertainty, it is basically blurring the rain over two different cities. The classification model will say that it will rain 30 millimeters per hour with a probability of half, but in each city. This could actually mean four different things. One, it rains in London and it rains in Brighton. Two, it rains only in London. Three, it rains only in Brighton. Four, it doesn't rain, there is sunshine in London and in Brighton, each with a probability of 0.25. It makes no sense, and it can lead to wrong estimates of accumulated rain prejudicial for flood forecasting. And the problem is that both those estimates will have a CSI, critical success index, of 0.5, which is actually good. So how can we fix the model and the evaluation? What went wrong with our baseline models is that they directly predicted grid cell, pixel-wise, rain rate probability, and that were trained discriminatively with a conditional independence assumption. They optimize rain at each pixel location from the point of view, let's say, of someone with a garden who wants to know it's going to rain over the garden, above the garden, but without the whole picture of rain across the country, something that meteorologists care about. What we need are generative models that can produce plausible realizations of rain and derive statistics from them. I forgot to go for my slides. So we need those kind of models, generative models. How do you model them? Deep generative models of radar. So, as I have motivated for already half of this talk, we would like a model that is consistent across spatial and temporal scales, that captures rare events and that properly accounts for uncertainty. Basically, what we want is a sort of a neural sampler that generates multiple realizations for a given prediction. We can then calculate the uncertainty of those predictions for multiple realizations, which is why we settled for the conditional generative adversarial networks. We build upon the work of our colleagues from DeepMind, who published previously Big GAN for generating images and DVD GAN for video prediction. Generative models are a very popular class of algorithms that learn to approximate the distribution of observed data X and to generate samples XS from that distribution. They are built using a deterministic model, like a neural network, and incorporate stochasticity through latent random vectors Z. When fed with a random vector Z sampled from a multivariate Gaussian, they can generate samples from that learned distribution. Conditional generative models predict a realization XS that is conditional both on the latent random vector Z and on a conditioning variable Y. Variable Y could be the past radar estimates of surface precipitation, and variable XS would be the future instance of precipitation. And a specific type of generative models, called generative adversarial networks, relies on adversarial training to train both the generator and the discriminator between output XS from the generator, the fake, and any real target image XR from the dataset. So in our model, we would feed 4 consecutive radar observations, previous 20 minutes, as context for a generator that would then sample multiple realizations of future precipitation, each realization being 18 frames long, covering 90 minutes. During training, the generator takes inputs that are 256 by 256 and outputs frame that are also 256 by 256, but we can optimize the loss only in the central 64 by 64 to account for cloud movements. Learning is driven by 2 loss functions and a regularization term. The first loss is defined by a temporal discriminator, which is a 3-dimensional convolutional neural network that aims to distinguish observed and generated radar sequences. It imposes temporal consistency and penalizes jumpy predictions. The temporal discriminator takes a random 128 by 128 crop out of a generated or out of the real radar sequence. Then the second loss is defined by a spatial discriminator, which is a convolutional neural network that aims to distinguish individual observed radar fields from generated fields, and it ensures spatial consistency and discourages blurry predictions. The spatial discriminator takes a random set of 8 frames, real or generated, that we have subsampled by a factor of 2, and applies the loss function. And finally, to improve accuracy, we need to introduce a generalization term, a regularization term that penalizes deviations at the pixel level between the real radar sequences and the mean of the predictions given by the model. So we compute the mean from multiple samples and multiple realizations. And this third term is very important for the model to produce location-accurate predictions and to improve performance. Otherwise, we just generate pretty pictures. And as a matter of fact, we can think of this third objective as the primary prediction objective, like in all other work, and consider the 2 GAN losses as regularization terms that enforce spatial and temporal structures. These 2 discriminators share similar architectures to existing work in video generation. Okay, so now let's go deeper into the generator. The generator comprises the conditioning stack, which processes past 4 radar fields used as context, and the conditioning stack allows information from the context to be used at multiple resolution down to an 8x8 map. It produces a context representation that is used as an input to the sampler. The sampler is a recurrent neural network formed with convolutional gate and recurrent units, GRUs, that use the context and latent representation as inputs. The sampler makes predictions of 18 future radar images. The output of the conditioning stack, that is fed as input, can be seen as the initial conditions for the sampler, like the initial conditions for an NWP. The sampler, of course, needs a source of stochasticity. which comes from the latent conditioning stack. That takes samples from a Gaussian distribution that covers a spatial 8x8 map and reshapes that noise into a second latent representation that is added at every time step to the convolutional GRU of a sampler. And those additional latent variables account for the uncertainty in the model. Okay, so that was the model. If you want more information, you can get it in the paper, and I'm also happy to answer questions by email. We train and validate that model on random samplings of crops from the radar between 2016 and 2018. At training time, we use an important sampling scheme that creates a data set that is more representative of heavy precipitation, and that enables us to capture rare events. We evaluate our model on a test set of full-frame images from 2019. Because our model is fully convolutional, we can apply it out of the box onto much larger radar frames that cover the whole of UK or the whole of the US in our supplemental experiments. Both the radar conditioning and the latent variables conditioning are convolutional, and that enables to training on small crops while having spatial-temporally consistent predictions during evaluation. Unlike methods like MetNet, we do not need to tile and to stitch small predictions to cover the whole frame. And importantly, once we have trained the model, typically on a TPU, but it also works on a more recent GPU architecture, we can do full resolution nowcast inference in about a second on an NVIDIA V100 GPU or 25 seconds on CPU. So how does this work? Our first metrics are the critical success index, which I already mentioned, CSI, which measures the location accuracy of a forecast at various rain rates. And we show here statistics at 1, 4, and 8 millimeters per hour. CSI is a ratio of true positives in the numerator to the sum of true and false positives and false negatives in the denominator. We can see that all three deep learning systems, UNet, actual attention, the generative model, produce forecasts that are significantly more location accurate than the PySteps baseline in green. However, we know that UNet and actual attention make blurry predictions. And yet, CSI doesn't account for the different ways the model can cheat to score better. So that's when the power spectral density, PSD, becomes useful. And these PSD plots show that both the generative model in blue and PySteps in light green match the observations, the black dotted lines, in their spectral characteristics. These PSD plots also show that the predictions from actual attention and UNet have much less small-scale variability, which means that they are smoother or more blurry, and that it gets worse when we increase the prediction horizon. At 90 minutes, the effective resolution of UNet is no longer 1 by 1 kilometer, it is 32 kilometers, and for actual attention it is 16 kilometers, and that reduces the value of these nowcasts for meteorologists. Here I'm highlighting what's happening with blurring, the reduction of power spectrum, and another phenomenon which is due to sampling from the logits of the actual attention, which introduces high-frequency noise. I will get to that. So before we go to the probabilistic results, I wanted to illustrate the ensemble variability of the GANs, generative models, for 6 different realizations and at 3 different time steps. So it's t plus 30, t plus 60, and t plus 90 minutes. These are the 6 realizations. We can see that the differences across different samples are actually pretty small. If we compare it to PySteps, the operational baseline used by the Met Office, this variability is actually quite larger. So it's going to be interesting to compare the probabilistic performance of PySteps versus that of the generative model. Here we are. For probabilistic verification, we use the continuous ranked probability score, CRPS, which is the difference between the mean error and the mean intersample variability for different realizations. And we compute CRPS on the average precipitation rate across different realizations, and we aggregate it over regions of increasing size. When we measure at the grid resolution level, GANs, PySteps, and actual attention perform similarly. But when we increase the spatial aggregation, then DGMR, GANs, and PySteps provide consistently better performance. And DGMR, our model, is performing best at maximum precipitation. The actual attention model is significantly poorer for large aggregations and underperforms all other methods of aggregation at aggregation scale 4 kilometers and beyond, even if we try to rescale the output probabilities. So now let's use a single case study to compare the nowcasting performance of several models. And we focus on this difficult case, which was chosen by the chief forecaster of the Met Office, who was independent from the project team. This case focuses on convective cells in eastern Scotland with intense showers over land. Yeah. Traditional methods, such as PySteps, essentially try to apply optical flow, but can overestimate the rainfall intensity over time. Something that's not observed in reality and doesn't sufficiently cover the spatial extent of a rainfall. The UNET model roughly predicts the location of rain, but because of aggressive blurring, it overpredicts areas of rain, misses intensity of rain, and fails to capture any small-scale structure. And the same can be said of actual attention, MetNet. When you try to sample from the logits of the actual attention model from MetNet, feeding them through a softmax, and after calibrating the temperature of that softmax on a validation set, we always end up adding unstructured noise because of that wretched independence, conditional independence assumption. But we do not improve the spatial details of the generated radar image. And we tried hard. We actually tried to use Gaussian copulas to have some structured, spatially and temporally structured noise, but it became even worse in a different way. By comparison, generative models preserve spatial structures, and they represent the convective events very well, and then maintain heavy rainfall in the early prediction. Unsurprisingly, when we showed these nowcasts to expert forecasters, they preferred the predictions made by the generative model. And this case study highlights a limitation of using existing metrics to evaluate forecasts. These metrics implicitly assume that the models, like NWPs or advection-based steps, preserve the physical plausibility of forecasts. But deep learning does not incorporate any physical knowledge, and it's much more flexible. So it can gain these metrics and outperform other systems by cheating, but still fail to produce useful predictions. So we need to be very thoughtful about the application of deep learning, because metrics do not allow us to discriminate between different approaches. Expert meteorologists can, because they have that knowledge. So that is the last section of this talk. We designed a new type of controlled study of expert judgments to assess the performance of nowcasting methods, because we want to assess the performance, so we assess the preference of 56 Met Office expert meteorologists. Office chief forecaster, who did not participate in the study, to design the study and to adjust the types of assessments. And we also submitted that study for ethical review by an independent ethics committee. Our hopes were that using expert verification, we could gain insight into the usefulness of machine learning in an operational setting. Can it help humans make better decisions on the development of new machine learning approaches for nowcasting, for instance? The experimental protocol had two phases. The first one was about preference ranking of predictions coming from 3 sources. Participants were provided a user ID before the experiment to preserve anonymity, and then they were shown a total of 23 cases of high precipitation data, more than 5 millimeters per hour, all cases selected by the chief meteorologist. So that's what they would see. On the left, observation at t+0, date, time, and geographic context. In the middle, ground truth at t plus 30, 60, and 90 minutes, and 3 comparative approaches to nowcasting. Optical flow-based system used by the Met Office, STEPS, deep learning baseline, the actual attention model, and generative models, always placed in a random order. And there was a color map scale for reference. And on the right, a form. The participants were asked to rank their model predictions compared to the ground truth. So they knew, so it was not a Turing test, they knew actually what the answer was. And they could also leave comments. In this operational setting, forecasters would often use multiple sources of information to make decisions. We opted to limit additional information to ensure that we can control the experimental conditions. After phase 1, we selected a random subset of participants for phase 2, a retrospective recall interview in which we asked to review rankings from phase 1 and ask questions based on their decisions. During that interview, a researcher running the interview tried to build a picture of the cognitive processes for decision making and what were the important features, and made use of recall of a task, details of emotive reasoning behind decisions, blanks, mistakes. The researcher would take notes during the participant explanation and then show those notes to the participant. The results of the whole study were drastic. Forecasters selected the proposed method, which we propose, the generative model, the GANs, as the most preferred, at 90% basically, with the next most selected being STEPS, the model currently used by the Met Office. And actual attention came a very distant third. The key factors for meteorologists included the ability to capture well the extent of rain, even when the intensity was not quite right. And those results contrasted with the quantitative verification scores that didn't give enough indication of difference between competing approaches and often favored models that blurred the forecasts. We also had some transcript extracts, but I guess in the interest of time, I would rather take questions. You can read those transcript extracts in the paper. So, before I finish, in summary, we're happy about running this operational assessment. We believe that its success could inform both how we run experimental psychology studies in atmospheric sciences and how we gain insight in meteorological decision mechanisms. And most importantly, we aimed at delivering value in an operational context. So, in conclusion, nowcasting fills a gap of performance for NWPs, numerical weather prediction models, in the first 2 forecast hours. And nowcasting highlights a role for machine learning that is complementary to existing physics-driven and simulation-based approaches. Of course, we are not interested in replacing human expertise. What we are interested in is empowering human experts with useful tools. Deep generative models like GANs can improve upon deterministic nowcasting methods. And they're able to provide ensembles, probabilistic ensembles, required to estimate the evolution of chaotic systems. And they're also suitable for high-intensity events. For instance, knowing the uncertainty of precipitation nowcasts to estimate the quantity of rain accumulated over a catchment area. And yes, as I said, finally, we want to keep the human in the loop. We want to provide genuine decision-making value for real-world experts, and we built the first deep learning model that significantly was preferred to an operational system by professional forecasters. And we hope to add to other opportunities and collaborate with you to build tools that are useful. Thank you very much. You can play with our model, with corresponding data and collab on GitHub. And I left my email here. Thanks.
Thank you so much. Brilliant presentation. It's so nice to hear these things spelled out so clearly, and it's actually beautiful to see the session start with a member of a national meteorological agency highlighting how the meteorologists and the AI researchers need to work together, and then see you coming from exactly the other side, but arriving at the same conclusion. So thank you very much. Are there any questions from the audience? So Jussi Lainonen is asking, wait a second, I scrolled away too quickly. He said, having worked a lot on GANs and atmospheric data, he has lots and lots of questions, but his simple first question would be, did you try to see if meteorologists could distinguish real rainfall from the GAN output?
Of course we did.
And how did that go?
I mean, it did work in the sense that it was kind of hard to distinguish. But,
for snapshots or for time series?
For snapshots.
Okay.
For time series, a little bit less.
Mm-hmm.
I would argue that the Turing test by itself is not very interesting because simply of the experimental conditions in which it is conducted. Mm-hmm. And because at the end of the day, we're not interested in fooling anyone.
Sure.
Yes.
I think coming back to the original question, I think my curiosity would be whether the spatial patterns that it captures from a single frame are captured as well or better than or worse than the time patterns in a time series. And I was actually wondering, when you're trying to learn these two aspects of the data, how do you tune the trade-off?
Yes, so this is essentially the trade-off between the two loss functions, the temporal and spatial.
Okay, and how do you set it?
We didn't really spend too much time optimizing the coefficient of a loss. One thing, as an anecdote, we noticed is that, unfortunately, the generative model ended up generating artifacts. Radar artifacts. So the kind of radar artifacts we had in our data was the flickering that happens, I think, when there's a flock of birds that passes next to the radar and then just casts those rays. And so in some cases, GANs would generate that, which is obviously and with the right flickering. So I would almost think that this was almost a disheartening example, because it's not what we want to get from the generative model.
Okay, well, it's realistic in another way. Yeah. There's another question by Mario Kren from a completely different angle, who's very curious about your impressive systematic questioning of domain experts. And he was wondering whether you involved any techniques from the social sciences to avoid biases or other weaknesses in your survey.
Yes, thank you much for this question. So actually, we did. I didn't put it in the slides, but there were multiple iterations with both the participants of a team from the Met Office and the chief meteorologist about the exact phrasing of the question. And this is also one of the reasons why we excluded the idea of a Turing test very early on.
Yeah.
The process in which we conduct those sort of experiments at DeepMind is that we have an internal review board, and then we submit to an external review board, and there's actually a whole team of social scientists and philosophers working at DeepMind on the various aspects of AI. One of the co-authors of a study, Shakir Mohammed, is very active in social technical AI research. So that's kind of taking it a little bit to a broader context. Yes.
Right. There's a question by Alexandra Grutza regarding your work on the data from the US, and I think more generally on any geographical setting where there are quite strong differences between regions in terms of how much rainfall there is. So if you have a region that is very dry compared to another, how well did your approach work in areas where rain is very, very rare? Because you're tuning it to capture the less frequent events, but how well does this work when the events are really rare?
I'm not 100% sure what the I don't recall doing a specific analysis of individual cases over the US. We just did a more general assessment, globalized. So I would presume that yeah, very rare events are still or even more a problem in the US than in the UK. Right.
Yeah. Yeah, it rains even in East Anglia, right? But yeah, okay, very interesting. There's a question by Christian Eichenberger, where he wonders if you understand correctly that the 4 input frames to the generator have the same spatial extension and resolution as the generated output. And if yes, he wonders whether you had any thoughts on why no further spatial context is required.
Right. So that is it's actually the same problem as for units that can have, let's say, 256 by 256 input window and 256 to 56 output. So we kind of circumvented that question by letting the model make a prediction over a wider area, because you want the model to work convolutionally, but optimizing a loss only in a central crop, because we would assume that the model would not have enough information to predict what's happening on the edges because of the movement of. So
you predict the whole area, but you're scoring in the center.
Yes.
I really liked your analysis and dissection of how choice of loss affects what you're getting. And I was wondering, now that you've been through the whole process once, including the interaction with the experts, if you were to start now, what would you do next? How would you adapt your approach in terms of picking a loss, setting metrics, doing these trade-offs? For me, it's been incredibly insightful listening to your discussion. And I was wondering, with all the things that you know now, what would the next steps be?
I guess for if the problem was slightly different, we would try to see how we can quantify, if it's possible, expert knowledge. And of course, it was a bit difficult in the case of the spatial temporal patterns that were assessed by meteorologists.
Yeah.
We did spend a lot of time trying to come up with new metrics. And essentially the best one we could come up with was power spectral density, because it was simply assessing these frequencies at different scales.
Right.
Yes.
Okay. Regarding the comments you had from the expert interviews regarding that the extent is more important than the intensity, that would sound like a straightforward mask approach where you just say, where is it raining with some threshold. What I don't understand at all is, maybe you can comment on it, what is the most valuable aspect in terms of the time modeling, the time resolution? Is it worse if you're off by a few minutes, but you get the event right? Or is this less bad if you're off for a few minutes, but you get the event right? Or is it important to get the start right, but then what exactly is happening and where is not so important? Firstly, I'd love to know what you've learned from the meteorologists on that. And secondly, assuming either way, which way the answer goes, how would you go about adapting metrics to all these different possibilities?
Yes, so we added this economic utility metric that essentially consisted in calculating the accumulated amount of rain over areas. And that has the advantage of not binding the model to making specific predictions at the right time, but essentially making predicting the right pattern of rain over a wider area across time.
Yes. Okay.
So that was so that is a metric that is probably a little bit more difficult to optimize, but it does correspond to this to economic utility.
Right. So you go right to the end point. Okay. There's another question by Christian Eichenberger. If you had to make a prediction for a larger area, how would you do that so that the prediction is consistent over the full area?
So the model, the generative model that we built, but same also for the unit, is fully convolutional. It is if you just feed it with larger inputs, it will symmetrically predict larger outputs too.
Okay, fair enough. This entire question of picking the metrics for the different questions. I mean, this is a beautiful showcase for weather, right? But actually, the same questions apply to so many other domains in AI and machine learning too. I was wondering, from all the other domains in which you've worked, because you have a very diverse set of areas where you've been pushing the state of the art, are there any advances happening there? Because it's a discussion that I really see, and I really enjoyed it.
You mean in terms of metrics?
Yeah, picking an appropriate loss, how that affects the nature of the prediction, whether that's the over blurring or getting certain things right or certain things wrong.
Yes, I'm actually interested currently in text generation for multiple reasons, and you can optimize the perplexity, or just the log likelihood of a model for making prediction of the next time step. But how do you optimize for the model to make sense, to generate sensical answers? How do you optimize it to maintain consistency? We've been essentially using next step log likelihood as a building block, hoping that if you just chain it over a long chain, maintained with a sentence that is still likely, and so on. But that is definitely a domain where we are short of metrics. So one way of circumventing this, I'm thinking of some work by a colleague of mine many years ago in language generation at FAIR, Facebook AI Research, Macario Ranzato, who started the whole idea of optimizing text generation using reinforcement learning. So you have a non-differentiable metric, you have a reward function, and you try to optimize the system to produce an answer that makes sense, but you don't necessarily know how to compute the gradient from that answer, that label, back to your model. And that's also what we use all the time in robotics as well, learning from human preferences. So if at least you can collect expert data and annotations, you could try reinforcement learning.
Nice thought. I hadn't made that connection. Yes, very nice. Are there any other comments or questions from the audience or any of the other speakers of today's session? And I think we're just on time. Thank you so much, Piotr. Again, I really enjoyed both the presentation and the discussion. And let me thank the speakers from the remaining session and from the first session as well. We had a fantastic day. Thank you so much for joining us. And I hope we see you at future iterations of either this competition or related competitions as possible in the future.
Thank you
very much.
It was fantastic. Thank you. It was an honor.
Thank you. Thank you so much. Bye-bye.